his name was Charles Messier. He was considered as a comet hunter. His job was to observe the comets in the sky. So whatever the objects I mentioned earlier in the initial slides, like stars and planets, it's a point source. If you observe it in the sky, you will see a single point of light. That will be stars or planets. So when it comes to comets, there will be a beautiful extent or tail to that. We can observe it time to time. So the image that I gave is, I think it's Neowise, which recently passed through nearby, and we were able to observe at some parts of the world. So it was his job to observe the comets. While doing that, he observed something special. So he was looking into extended objects in the sky. So what he saw is like some other extended objects which are not comets. So he categorized it. He didn't know what was that. He considered it as part of our galaxy, some star-forming regions or some open clusters of stars, like that. So these are the Messier objects, but some of the Messier objects among 110 which he observed at that time. So the image is taken, it's not Messier's images, it's from the Hubble Space Telescope. So as you can see, there are some magnificent images which is having some features like spiral or some globe is enlightened or enlarged, like that. In that, there were some candidates like M31. So when he identified this object, he named it after him. So when you identify a comet, you can name after it. Right now also, if you are identifying a new one, you can name it like Ujjwal's comet or Robin's comet, whatever you want. That's why Halley's comet is also there. So he categorized these special structures that he saw as Messier objects or M objects. He numbered it from 1 to 110. So these are two special structures that he saw, special objects he saw in the sky. One is M31 and another one is M74. That's the name that he gave. So some of the important important things about the image is we are seeing something that we didn't see at that time earlier anywhere. So there was a confusion. What are these objects? So in the case of science, if you have something, if you identify something, you will be connecting it with the existing theories. So at that time, most of the people thought like this is part of the Milky Way, our galaxy itself. These are some star-forming regions in the galaxy. That was the initial idea. But as the time passed by, research was done in the direction of these specific objects. Some of the other people, some of the researchers thought or introduced an idea that these are not part of our galaxy. These are island universes or not part of our universe. The point is like the universe idea of that time is our Milky Way only. So whatever we saw beyond that, those people considered it as island universes. So the researcher but didn't conclude that these are island universes or the name galaxies wasn't coined by that time. A breakthrough happened in the Great Debate time. So Great Debate was like there was a meeting of astronomers and we will be discussing about the ongoing science projects and science works at that time. In 1920, there was a meeting in which two of the people who were pioneers of both the ideas, who says the spiral nebula at that time, what they called it, is part of our galaxy and not. So Shapley and Curtis was the main people who were having the thought, and they were having a debate. It is considered as great debate. I don't know why, but it might have been a great debate. So they are in fact, in Shapley's consideration, he was the old school. So he considered it as nebulae are relatively small and lay within the outskirts of the Milky Way. It's basically the part of the Milky Way. He put forth some points based on research, which was limited to that time, the observational evidence, which was limited to that time, and he was proposing that these nebulae are relatively small and part of the Milky Way. But Curtis, based on his inferences and his studies, he opposed it and saying like they are in fact independent galaxies, implying that they were exceedingly large and distinct. But at that time of this debate, an answer to the problem, this particular problem was never, it was not concluded. Both of these people published papers in the coming years, one by one. Basically, it was like a Cold War. They were refuting the theories the other guy put forth. An answer to this question was introduced in 1924. So there was a guy who was looking into these objects in the sky, like the specific objects which are considered as spiral nebula at that time. And M31, which I showed earlier, it's one of the nearest galaxies to our Milky Way. Now we call it as Andromeda. So he was able to observe some variable stars. So variable stars means if you look at a bright source, if the light is coming, the brightness of the source is continuous, you want the brightness you are recording will be same only. If it varies in period, they consider it as variable stars. There will be a period for that and all. So based on Cepheid variables, he estimated the distance to Andromeda, one of the Cepheid variable stars in Andromeda, and he was able to estimate the distance. So he found out that the Andromeda is located far outside the Milky Way. So to the answer to the question of the great debate, Curtis was right, which means it's beyond the extent of the Milky Way. They are island universes, or now we call it as galaxies. So the year was 1924, all this happened. So we are talking in 2022. So it's not at all 100 years that we celebrate this thing. So the guy who is looking through the telescope is Edwin Hubble. You might not have known about his name, but this guy, but recently, since the James Webb Space Telescope came, the name Hubble was all over the news because it was the predecessor, Hubble Space Telescope, which was named after him because of the contributions he made. So he is holding a picture of the Andromeda galaxy representing the variable star he used in that figure. So he didn't stop there. He estimated the distance and he didn't stop there. He knew we are doing something extraordinary. So he observed all the objects, extended objects he can by the telescope, which he had a private access to, and observed all the whatever the extended objects were available. And as humans, whatever we get, we have a tendency to classify. We want to group it together. So this guy did the same thing. So there are galaxies which are having different shapes. Based on that shape or the morphology, Hubble classified these galaxies in this order. So there are elliptical galaxies which does not have any feature or anything. You will see as an ellipse patch. And there are some differences based on the extent and all. He classified it E0 to E7. Then there are spirals, which is having the spiral structure around it. If you have seen the image of Milky Way, you know what are spiral galaxies. There will be a spiral structure around the bulge. And he classified it according to the strength of the arm and winding of bar and all, SASBST. Then there was a possibility that a bar is present in the inner part of the galaxy or the spiral galaxies basically. So he classified it again as spiral barred galaxies, SBA, SBB, SBC. So S0 is basically lenticular galaxies. It's not elliptical. It's having a shape something like for lindil. It's a edible thing, lindil. Its shape is like this. So most of the time what we consider it as lenticulars. It's a transition state between these two type of galaxies. And there are some galaxies which he couldn't give a particular shape to. So he considered it as irregulars. That's classified here outside the tuning fork diagram. So it looks like he arranged it in a tuning fork manner and we call it as a tuning fork diagram. By that time, his idea was like the evolution of galaxies happens from elliptical to spirals, which means his idea was like there will be a spherical structure. Following that, the spiral arms will be forming. So the evolution will be in that order. That's why he arranged it like this way. So he classified it as early type galaxies. Early type galaxies means it's in the initial stage. So he considered ellipticals as early type galaxies and spirals as late type galaxies. Even though now the idea changed, we are still using the same etymology. We are considering early type galaxies as ellipticals. So we'll come to that point. So the idea was evolution happens from ellipticals to spirals. So we'll look at a simulation of our Milky Way's fate. I will start from here because it will be easier for you to understand. So it's a simulation done by some astronomers from NASA, I guess. At that point, they were considering what will be the fate of our Milky Way. So you can see the Milky Way and the Andromeda galaxy or M31. And at some point in the coming after billions of years, these two galaxies, because of the gravitational attraction between them, it will be merging or colliding each other. So the resultant you can see in this simulation, the initial collision happened, but still the gravitational pull will be there. This is a simulation only based on some inferences. and might be something like this will be happening in the future. So after colliding again and again, you can see the spiral galaxies, which are M31 and our Milky Way. It will be forming or it will be resulting as an elliptical one. So, and based on so many research, we know that the evolution is from spirals to ellipticals. That is, spiral galaxies will be formed first, then it evolves into elliptical galaxies. So, we want to understand how that happens. So, these are two galaxies. One is an elliptical galaxy and the other one is M74. So, an spiral galaxy. If you as the technology advanced, we were able to understand the properties of the population present or the ages of the star population in this region. So what they found out is in the elliptical galaxies, if you look, you will be seeing older population of stars or older systems. But in spiral galaxies, you are seeing younger population of stars. So if the evolution is ulta, like elliptical to spiral, it won't be the scenario. So now we know the evolution happens from spirals to lenticulars based on the population after studying the age of the population in in different types of galaxies. So that's the still it's in debate whether how to study the evolution of galaxies. So the key, one of the keys is star formation, which we can directly know. So star formation means number of stars or stars are being formed in the galaxies. In our galaxy also stars are being formed. One of the Carina nebula's image provided by JWS is given here. So in the classification itself, what came up is like, we know the evolution. Right now we know the evolution is from spiral galaxies to elliptical galaxies. So in terms of star formation, spiral galaxies are still star forming, but elliptical galaxies are quiescent. So stars are still born in blue regions or spiral galaxies. Stars are not being born in quiescent galaxies. So if we want to know the evolution, we want to learn about or know about how the stars are formed or what are the factors affecting the star formation. So the result is like there is gas which forms stars in spiral galaxies, which is in the nascent stage or in the initial stage of galaxy formation. At some point, the gas in the system is converted to star or ripped away from the galaxy and results in elliptical galaxies. So that's the evolution sequence. If you want to learn about it, we want to look into the star formation happening and the factors affecting the star formation. So based on all these studies, right now we know there are two types of factors affecting the evolution of the galaxy. One is secular effects. Secular effects means the structures inside the galaxy itself is driving the star formation or ripping apart the gas, whatever. So spiral structures and the presence of bar, all those things could affect secular effects. But environmental effect means mergers. Basically the mergers. We saw that animation of Andromeda and Milky Way colliding to form Milkomeda. I think so. That is the name they gave, Milkomeda. So mergers will be happening. So this is another structure we can see in the sky. This is M51. So a new galaxy is colliding with the other one. A small galaxy is colliding with the other one. It's still existing as another galaxy itself. So this is not a single galaxy. It's an interacting system. So that comes in the merger scenario. Now we know star formation, we can use the star formation to identify or trace the evolution of galaxies. Now we want to quantify or estimate the star formation happen. For that we need tools. So for astronomers, what we get is only light from these objects. We want to make or we need to do the science based on the images or the spectra that we are getting from this object. We can't go there and analyze what happens there. Okay. So for that we need data. Here I have represented, there are, I forgot to include one more slide. So based on the mass of the stars, stars are classified OBAF, GKF. So mass decreases. So mass decreases means temperature also decreases. So temperature will be higher in the massive star, O or B or A type of star. So it will be 3 times greater than the mass of the sun and all for these type of stars. So if you know, since this is massive, the temperature is also higher. Since the temperature is higher, if you remember the black body diagram, I think all of you are from physics. So if you remember the black body diagram, most of the, if its temperature is much higher, the light will be, black body will be peaking in the UV region. So light we are getting from these stars will be in the UV region. Why these stars? Because since these are massive stars, they are short-lived. So mass, as the mass increases, the nuclear fusion will be increasing and the stars will be formed, stars will be evolved out of the main sequence, or its lifetime is short-lived. So short-lived here in our case, we mention it as 100 million years. So less than 100 million years. We deal with million year scale because stars are being born and lived up to millions years or giga years. Here these stars will be living in 100 million. So if you can quantify the UV light, consider the UV light that we are observing in the sky is coming from the massive stars only. We can consider that as the light coming from stars formed within the last 100 million years. So then if we can quantify it, you can connect it with the star formation happened in the last 100 million years. That's what we are trying to do. I think the idea is clear there. Since the age is lesser, whatever we get the light, we consider it as the recently formed star. For that, we need telescopes. So I mentioned about it will be emitting in the UV region. We can't observe these ultraviolet continuum in Earth because of the ozone layer and the atmosphere and Earth. So for that, we need space telescope. So now on, I will be talking about my work, my recent work. So ultraviolet imaging telescope is one of the 5 instruments on board AstroSat. So AstroSat is India's first space observatory dedicated for multi-wavelength astronomy. So you can see the image of AstroSat here, and it's having 5 instruments including UV-80. But I am interested mostly in UV-80 because I want to learn about star formation. So this is the AstroSat diagram for AstroSat. Basically, it observes when you have a telescope. If you look at the sky, you will be seeing the light coming in the visible region only, like whatever your eye can observe. So that wavelength will be, say, let's say from 300 nanometers to 600 nanometers maximum, 300 to 500, 550. So if it's ultraviolet, we want to observe it in 2 different bands. We will be dividing the ultraviolet region into 2, and the telescope will be receiving only 2 windows. Like for FUV, if the light comes in between 130 to 180 nanometer from an object, it will be considered in the FUV region or far ultraviolet. In the NUV, if the light comes from 200 to 300 nanometer, we will consider it as NUV. That's what the telescope does. So I'm not going in detail about this, but why are we using UV-80? Is it because it's only our telescope? No. So predecessor to UV-80 was Galaxy. It was launched by NASA. So I have given comparison images. So we will be getting images only. We are taking the photo of the galaxy or the region that we are interested in. So in the left panel, I have shown the galaxy image for a particular region in M31. That's the Andromeda that we were talking about. And this one represents the same region UV-80 image. If you can see in galaxy, if you look at this particular region, you are seeing patchy regions only. You are not able to see the finer structures. Since if you look at this particular image, in the same region itself, UV-80 is able to resolve that patchy region into 4 or 5 components. That's basically the resolution. The resolution difference is making the difference. So resolution means whatever the spatial resolution means whatever the size we can resolve up to in the sky. So for UV-80 it's much higher. We can resolve finer structures than galaxy. That's why we are trying to make use of UV-80 for this particular slide. So this is the galaxy I was working on. This is NGC 628. So it's a famous galaxy, and if you look into any astronomical surveys, it will be one of the first galaxies that the telescope will observe. So it's near to us, and we have a dearth of literature about this galaxy. The image that I showed here is the color composite image of FUV and NUV images that we obtained from AstroSat or UV-80. So this is just a photo. That's it. It's a color composite image of NGC 628. Now the second stage is we have the image. We want to identify the star forming regions first. Then only we are able to quantify the star formation. For that we use R programming language based Proform to identify the star forming region. Not going into detail. So it will give you an output of star forming regions or bright points in an image that you gave. So the bright points in UV will be connected with the clusters or star forming regions. That's the idea. So interesting fact is right now we are looking into the spiral lamp. In this study we are looking into the spiral lamp. How the spiral lamps affect the star formation. There are some previous studies on the spiral arms of NGC 628. That was the driving force us to look into this in UV80. So here are some facts about Gusev and Shabani. Gusev looked into this galaxy in the using the Galax, and there is Hubble Space Telescope (HST). Shabani looked into it using HST, and they studied the properties. One of the important results from Gusev is was that the properties of the star-forming regions in the spiral arms differs. Like if you consider the blue wala one as the arm A and consider the red wala one as arm B, he consider only the red region, Gusev. The star formation or the properties of the star forming regions are different in these arms. For a single arm, it's okay. When you are comparing it with the properties of the star forming regions, the other arm, it's different. That was his conclusion. But his study was limited with the resolution because he was using the galaxy. And he didn't consider after this point. So it's studied that before 1 giga-year, there was an interaction happened in this galaxy. Because of that this particular arm was disrupted at this point. So when Gusev studied, he didn't consider that portion because it's disrupted and he didn't include. But when Shamadi studied, he was limited with the field of view. The entire galaxy was covered in Hubble Space Telescope's images because the field of view was lesser. So in our study, we are trying to understand the properties of the arms and compare whether there is a difference. If there is a difference, what could be the reason? So we identified the star forming region using some population synthesis models. We can estimate the age and mass of these star forming regions. I used Starbus 99. So not going into detail, we estimated the age by making use of the UV80 images that we have. And we tried to plot. So in the figure, I identified the arm A components and arm B components in both the scenarios. As like Gusev did, in red, I only took whatever star forming regions are there till the disruption starts. In the next condition, I considered the entire arm. So that's the two plots that you are seeing here. In the left panel, arm B is shorter arm, which means only the red till the red points was used in arm B. In the right panel, I compiled blue and green regions which I showed. So what you can see is if these are two different populations. This is the KDE plot. You can assume like an histogram plot. If you plot an histogram of different population, it will be having different distribution. That's the idea. For here, we are using KDE plot for the density representation. And here also what you can see is like, in case of star formation rate density, both the regions, we are seeing like there is no difference. The properties of the star formation even if you are considering arm B as shorter one or the longer one, the distribution is same. It's a single population only. We can't distinguish it as different population. But when it comes to the case of age, you can see a distinction is there. If you are considering the short arm concept only, there is a small distinction between this. And if you are considering the total extent, that distinction fades away. So we did the KS test also. The results from the KS test also suggested the same. So at that point, we looked into the spatial distribution of age and mass in this region. So this is a UV80 image overlaid with the star forming regions identified along with the age and mass associated. I'm not sure the color is visible for you. I will just explain it. So if you look into the image, the younger population, or we'll start from inner, the older population is dominated in the inner part of the galaxy. And as we go out, radially out, we are seeing younger population. I think the color is not visible here, but that's what happens here. In the case of mass also, massive regions are located inside, in inner region, and less massive regions are associated or in the outer region. That is basically because there is a consideration or theory that the galaxies are growing inside out. So the inner part of the galaxies will be formed first and the outer part will be formed later. So we will be seeing older population in the inner part of the galaxy and younger population in the outer part of the galaxy. So what happened with Gusev's study might be, he was considering on that till the disruption starts. So because of the inside out growth of the galaxy, since he reduced or only considered inner part of arm B, he was misinterpreting that there is a difference in the properties of spiral arms in NGC 628. So at that point, we were interested in the theory that they proposed. They proposed like the difference is because of the formation mechanism of the spiral arm. So till now, there are different theories, but initially the spiral arms formed in these galaxies was considered as part of the matter. The matter itself constitutes the spiral arms. So matter and the spiral arm is not different. It's single entity. Matter or stars or the gas or dust present in the galaxy forms the spiral arm. That was the initial idea. But there was a problem to that. So if you look here, this is an animation. So if that's the case and the orbital motion, orbital velocity is same for a star, after some time, the spiral arms will be disappearing. You will be seeing circles only. Because there is a difference, the orbital velocity is higher. So in the inner part, it will be rotating faster, the stars. Outer part, it will be lagging. So because of that, spiral arm should wind up. So that is the winding problem. But what we are seeing is a consistent structure like this. So at that point, it is required that we have to introduce some theories to make sure or confirm that the spiral arms are still present even if and the winding problem is solved. There came some other theories. One of the most accepted theories is stationary density wave theory. So stationary density wave theory was introduced by Lin and Chu, and there was a paper which is having so much derivation which I didn't even understand at some point, and we are not going for that at this point. Then I will come to that stationary density waves in soon. So another one is swing amplification. Swing amplification says like there are some perturbations there are here and there in the galaxy. Because of that, we are seeing some spiral structures. And bar induced and manifold were there. But mostly accepted is spiral density wave and swing amplification to an extent. So spiral density wave theory, basically how does it form is like the stars are revolving around, stars and dust and massive regions are revolving around the center of the galaxy in an elliptical manner. So if you consider the in a first ellipse compared to the second ellipse, there is an angle difference between the semi-major axis. So it's shown here. So let it be the first one. This is the semi-major axis of that ellipse, first ellipse. The second one, it's a little bit tilted to an angle. The other one, the next one will be tilted again. So if you increase that, the number of ellipses, you will get a structure like this. So this structure resembles the spiral structure, but matter is not constituting, or the stars or the interstellar dust or anything doesn't constitute that spiral structure. It's basically because it's a pattern formed because of the evolution revolving around the center of the galaxy. But is the star present in a spiral structure is the same throughout the life of the galaxy? No, it changes. If you see the rotation, the object will be moving away or moving in. The spiral structure is composed of different stars or different dust at time to time. That was the idea. I think that's it. So, according to that theory, if spiral structure or the pattern form is a stationary density wave, which constitute the spiral structure, the matter will be moving along the galaxy, right? So the idea is like stars are revolving around the galaxy, and there are spiral structures also. But the velocity of the stars, I will come to stars only. We are talking about star clusters here. For the easiness of conveying, I will talk about stars. So in the inner part of the galaxy, stars will be moving faster. So, and in the outer part, it will be slower, right? And in the case of spiral structure also, if a star formed in the spiral structure, because it's near to the inner part of the galaxy, stars will move away from the spiral structure. So you will see the older stars will be, or star clusters will be located far away from the spiral structure because there is a velocity gradient between these two things. The stars and the spiral structure is having different velocities. So because of that, you will see an age gradient if you are looking along the arms of the galaxy. So you can validate the spiral density wave theory based on this. So the idea is like if I can define a ridge line and I can calculate the distance to the star clusters that I identified or we identified. At that point, if I am seeing an age gradient, that means the spiral density wave is the reason for the star formation. I think that's okay for you, whatever I said. So for that we need a tool. That's why we use azimuthal distance distribution. Here we try to get the distribution based on age classes. So I classified it into three classes: age less than 30, 30 to 60, 60 greater than 60. At this point, what we expect is from the median value, we will be seeing an increasing or decreasing trend if it's a spiral density wave. But in this case, we didn't see that. So what we suggested is like spiral density wave might not be the only reason for the formation of spiral arms in NGC 628. So I'll summarize it here. So these are the summary of my work. We used FUV and NUV images of NGC 628 from UVIT and identified nearly 300 star forming regions. Younger clumps are in the inner part of the galaxy, and there is no significant difference between the spiral arms of NGC 628, and it is proposed that spiral density wave theory might not be the base for the formation of spiral arms in NGC 628. It matches with some of the literature studies. So this is the publication that we had in mnras about this work. You can look into the work for more clarification. And our research group is in my research group here. We are working under Sreeja and myself, Robin and Agil Krishna is part of it. We have collaborators from IAE and LMU Germany, Dr. Smitha and Dr. Koshy. Thank you. You have some doubts? Need clarity? Yes, sir. There are two scenarios. It can be stripped away. The gas can be ejected into intergalactic medium, or the stars can form stars. At that point, if merging happens, a starburst can occur. All the gas will be because of the shock, gas will be forming stars and in an instant rate. So that stars can be formed, or it can be stripped away, like raw pressure. What is that? So after billions of years, the stars will be already gone. Stars will be present in the star clusters will be present, but it will be older systems. Or yeah, it might happen. It was like a million years only, 1 gigayear maximum. Spiral should wind up. That's what I remember. Yes. If that interaction happens, there are two scenarios. Either the gas are forming stars, right? So gas can be stripped away. So the gas is injected into the intergalactic media. Otherwise, because of that, a new burst of star formation happens. So that image which I showed for M51, the recent star formation has increased in that region. At the tail of that, there was an intergalactic galaxy. Yeah, here. So it's not necessary that directly converts to spirals. There are some structures like polar ring galaxies, which Agil works on. It will form some finer structures around it. You'll be seeing some magnificent images at that time. So that is all it is. Yes. Sextractor, yeah. Sextractor. Sextractor to source. So here in the at that time when we were using Proform, when we identify the structure, the extractor consider it as an ellipse. When they are identifying the object, they consider it as an ellipse only. So when it comes to Proform, it gives you the structure properly. Like even if it's a curved one or some random kind of structure, it will give you that structure. So that's why we were sticking with profound. Now I guess sex factor is also giving that lecture. It is added to sex factor. We are not modeling it, sir. We are picking up the star forming regions. I think it's still, I'm not sure about that, sir, because of the mass is coalesced in the central region. As it rotates, the disk forms. Masses, masses objects are there, there will be a rotation happening to conserve the angular momentum. So yeah. That's yet to be understood. So we were the people were connecting whatever observed with theories. So it's not a concrete theory yet. Still debates are happening whether spiral densities are the reason for spiral structures or not. It was initially was an assumption, but for some of other galaxies, the age gradient that I talked about is already present. It's visible in some other galaxies, like M51 itself. Might be Milky Way itself, sir. No, no, we don't know. We don't know. It's standard. It's standard. There is a difference. That's the proposed theory. No, no, no. So you can see whatever we talked about is grand design spiral. You can see only two defined spiral arms. There are multi-armed spirals, which is having more than two arms, and there are flocculent spirals. There are spiral arms, but we can't distinguish separately. So that's another topic. Yeah. So basically, spiral density wave theory, if that's happening as they suggested, if you combine multi-wavelength images, you will see a gradient. So in the inner part, you will see the older population in the near to the spiral arms and younger population near to the spiral arm, older population away from that. As the radius increases, it shifts. So if you can combine IR images and UV images and merge it together, you will see that gradient there. So in the inner part, younger population will be in front, older population will be in the back. After some point, it will be ulta. So at that point, there will be the point at which that happens is defined as rotation radius. So there are so many mathematical explanations for this. No, 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 it's not moving out. The star is already rotating around the galaxy. But the velocity of that is different compared to the pattern or the spiral arc. So if you are rotating like different speed, after some point, if I am moving like this and the velocity is increased, spiral structure will be here and the stars are moving away from that. That's the idea. It's not moving from the spiral structure, running away from it. Yeah, that's possible because that's what we know, right? ISM, the material or the dust that we see in the ISM is part of is generated from the supernova expansion or explosion happened, and so it will be enriching it. But I'm not sure whether I answered the question. It can happen, but it won't be triggering another generation of star formation because the gas will already be uh, wiped out or stars are born. So it might not be forming another set of generation stars, but interstellar dust, the amount of metallicity will be increasing, basically.